In this second video on alkynes, we're going to look at the addition of various reagents to the carbon-carbon triple bond. And what we're going to see is that in many cases, those reagents that we're adding to the triple bond match those of Chapter 6. We're also going to look at how to make an alkyne where no alkyne group previously existed. And that's the first thing that we'll look at. And what we're going to see here is that we're just going to take the elimination reaction, dehydrohalogenation, out of Chapter 5, and we're going to basically just do it twice so that we make an alkyne instead of an alkene. Okay? All right, so here we go. Here is the first example of that. Before looking at this reaction, however, let's just remember that the most important way to make an alkyne is probably the route we saw previously involving the alkylation of terminal alkynes. So the best way to make a complex alkyne is from a simpler alkyne. Okay, when we don't already have an alkyne group, we can introduce one through this double elimination route. All right, so here we're going to take a dihalide. We can take either a 1,2 dihalide like this one or a 1,1 dihalide like this one. Okay, we're going to find that this route here involving the 1,2 dihalide is more useful because the only way we're ever going to see in this class for synthesizing a 1,1 dihalide is from an alkyne. So all we would do is reverse the reaction that made this dihalide in the first place. So this is not really going to be quite as useful. All right, so we're going to take 2 moles of a very strong base. Very often this base is sodium amide, like you've seen before. All right, we can also use potassium T-butoxide. Actually, let me just write it differently, T-butyl, sorry. Sometimes we're going to see that KOH, if we heat the system, will work as well. All right. What this reaction here, making the alkyne here, can be best described as a double E2. We're doing the E2 twice, okay? So let's not forget that in addition to this, we also had some hydrogens here that we left out of the bond line diagram. All right, so we're eliminating HX once and eliminating HX twice, and that is producing the alkyne. The same thing happens if we start with a 1,1 dihalide over here. It's just that all the hydrogens are on the same carbon and all the halogens are on the same carbon. All right, so what happens here? Okay, let me go back there. So potassium T-butoxide, remember that. All right, so what happens here is that our first mole of base is just doing an E2. All right, the E2 eliminating one of these HXs gives you this compound here called a vinylic halide. All right, and the second mole of base is going to come along and pull this proton off right here and do the E2. But since you already have an alkene when you do this E2, you go from a double bond to a triple bond. Okay? It's possible to stop the reaction here, but it's a little bit difficult. So what's usually happens here is that the reaction occurs twice, going all the way to the alkyne. All right. So let's think about, here's a classical transformation that we have to do. Turn an alkene into an alkyne. Okay? All right, so we know how to make the 1,2 dihalide, right, from an alkene. All you do is you add bromine or chlorine. All right, so when you add bromine or chlorine to an alkene, you get the 1,2 dihalide. And all we have to do is in the second step, we're just going to just treat it with 2 moles of, we'll say, NaNH2 maybe potassium tertiary butoxide. You might actually need 3 moles because if you used NaNH2 because your product itself is acidic. So you might pull that proton off too, and you'd have to add acid or add something to turn the anion back into the terminal alkyne if that got deprotonated. But that's we won't worry about that because virtually every organic reaction is worked up with water, and water is acidic enough to protonate a terminal alkyne derived anion. All right. We can add hydrogen to an alkyne, and of course there's an obvious issue here. When we add hydrogen once, okay, and in addition, we're going to get the alkene here. This initially formed alkene is of course going to be the cis geometry, just like you see here, and reaction doesn't necessarily have to stop here because this combination of reagents also hydrogenates alkenes as well as alkynes. Okay, so it's very hard to measure the amount of hydrogen that you put into a reaction. So if we're just doing this reaction the classic way with high pressures of hydrogen, we are going to more than likely see the saturated alkane as our final product. Okay. All right, so what has been developed are catalysts that are selective for just stopping the reaction here. One of the best ones is called Lindlar's catalyst. Lindlar's catalyst is just this combination of palladium, calcium carbonate, and lead acetate. All right, so you've heard that lead is a catalyst poison for your catalytic converter, and that's why one of the reasons it was stripped out of gasoline. The other one was that it was raining lead down all over the environment as well. So it's got some disadvantages. But what happens here is that we're poisoning the catalyst, but we're not poisoning it to death. We're poisoning it so it just has enough life to only hydrogenate the alkyne group, and it cannot hydrogenate the alkene group. Okay? All right. So we don't have to worry about the amount of hydrogen that we're adding to the system when we have Lindlar's catalyst. Add as much hydrogen as you want. The catalyst is not capable of catalyzing the hydrogenation of the alkene to the alkane. Okay, so the reaction will stop right there. In most equations, we get tired of writing all these reagents, so it's just shown as Lindlar's catalyst. Okay. If we want to make the transalkene, like we see here, we're going to use a different combination of reagents. We're going to use sodium or lithium and ammonia followed by ethanol. This results in the net addition of 2 hydrogens to the opposite sides of the alkyne, thus resulting in the transalkene. All right. If we look at where the hydrogens come from, they come from the ammonia and the ethanol. All right, so here's some equations. Let's imagine each of these cases has an alkene and an alkyne. Okay, so when we treat this compound with Lindlar's catalyst, it's going to ignore the alkene here. It's going to ignore this alkene. It's going to hydrogenate nothing but the alkyne, and it's going to add the 2 hydrogens from the same side. So syn addition resulting in the cis alkene. Okay. All right, so when we hydrogenate this one, we have an alkene that's not going to be touched by the reaction. So we're going to treat this with sodium and lithium or ammonia, then ethanol, and this is going to produce now the product here. And what we're going to see is that since the hydrogen's added from the opposite side, we get the transalkene. All right, an important other thing to note here concerning this reagent, it's not equal to NaNH2. These are different reagents. All right, let's briefly look at the mechanism for the lithium ammonia or sodium ammonia reduction of alkynes. Okay. All right, so I don't think I put this on the exam, but let's just look at it anyway. The pi bond is weaker, so what happens here is we're going to take sodium, and sodium has this extra electron. Remember, sodium wants to become sodium plus. right? So it can become sodium plus by getting rid of that electron. And one place that you can put it is into the into one of the unoccupied molecular orbitals of the pi bond here. This is going to give you the radical anion. What we have here is now a double bond, and there's a half a bond order between these two. This is now going to react with sodium, and this is going to produce the dianion. The carbanions are negatively charged, repulsive. They want to get as far apart from each other as possible, and they do that by existing on the opposite sides of the molecule. That's where our trans stereochemistry comes from. All right, so ammonia will definitely protonate the dianion, and I think the monoanion, it's a little hard to protonate with ammonia, so that's we have to have a stronger acid, ethanol in this case, to deliver the second proton, and that gives us the product. Okay, so down here, what we've repeated is this other this thing again. So remember that these are different reagents. Sodium and ammonia is an electron source. NaNH2 is a strong base. If you've ever done this reaction, it's beautiful. You take liquid ammonia, very cold temperature, like -33 degrees, and you add just one chunk of sodium to it, and you get this beautiful purple solution that's referred to as the solvated electron. And that's what essentially does the reaction. All right? All right, so let's do a little roadmap problem. Let's predict what we get along the way here. This has some things out of chapter 9 and it finishes off with a reaction out of chapter 6. All right, so the first one, it's important to remember that a terminal alkyne is acidic, right? So in this first step, we're taking the strong base, removing the terminal alkyne hydrogen, then alkylating the resulting anion with methyl iodide to produce the compound that has a methyl group on the alkyne. Now we're going to do the reduction. Okay, and the reduction. Remember, this is the recipe for getting a transalkene. Okay, so we're going to see that our product is the transalkene. The two hydrogens I've shown in red get added from the opposite side, therefore they're producing the transalkene. Bromine, don't forget from chapter 6 that it is an anti-addition. Okay, anti-addition. So we're going to add it from the opposite face. Okay, and the product that you see is this one, where the two bromines, remember, are opposite. This means the two hydrogens that you originally started out with go on the opposite side as well. So this would be the diastereomer that you form. You'd also form this accompanied by its enantiomer, since bromine and the starting alkene, of course, neither of them are chiral compounds. So when you produce a chiral compound from achiral materials, you make a racemic mixture. All right, we can add HX just like we did to alkenes. What we see is the same general ideas apply. It follows Markovnikov's rule. We get the X group at the more substituted carbon, the H at the less substituted carbon. But when you look at an alkyne, only a terminal alkyne has the ends different, okay? So in a terminal alkyne, like in the second equation here, when we add HX twice, we're going to see both of the hydrogens add to the less substituted carbon here, and we're going to see the more substituted carbon get both of the X groups, okay? In the internal alkyne, both of these carbons are equally substituted, okay? So if you look at each carbon all by itself, each carbon just has an alkyl group on it. All right, we're not going to expect any selectivity in this reaction, and we should see a mixture of both of these compounds. Okay, let's look at the second case here. This is the one that's going to be selective. All right, so what we're seeing here is that our initial protonation is going to give us either the secondary vinylic carbon, shown here, or the primary vinylic carbon. And just like regular carbocations from chapters 4 and 5 and 6, the carbocations that are vinylic here also are stabilized by alkyl groups. So this top pathway is the pathway that we're going to see. Bromine comes in later and produces the vinyl bromide that you see here. And this one you can see is obviously the result of a Markovnikov addition. All right, so this vinylic carbocations, they're not quite as stable as the carbocations you saw before that have 3 bonds and a positive charge. All right? Okay, and because of this, what we see here is that it's actually a little easier to add the HBr to this alkene than it was to the alkyne. Okay, so it's very hard to stop at this stage. Now we're going to see the Markovnikov's rule also followed, but for a different reason. Here the bromine is stabilizing the positive charge. Let me just draw those lone pairs here. Okay, so we have these lone pairs at bromine. Okay, and what we're seeing here is that they can stabilize the carbocation through that form that you see down there. Okay, so this is an example of a resonance stabilized carbocation. So this is also following Markovnikov's rule, and that is why you get both halogens at the same carbon. It's also why you get both halogens at the same carbon up here, because this carbocation adjacent to the halogen is a little more stable than the one that's not there, that's not directly beside the halogen. So when you add the second mole of HX, X also ends up where X already was. Okay, so that's why you see both in both products, all the halogens have added to the same carbon. Okay, all right. Hydration is also something we can do. If you think about what's the immediate product of water adding across an alkyne, you would say it would be this compound here that has an alcohol right on the double bond. And we're comparing that. This is the Markovnikov product. This is the anti-Markovnikov product. And these types of compounds where you have an OH right on the alkene is known as an enol. All right, so this is the immediate product of a hydration. But turns out that this is not what you obtain from the hydration process here. You obtain a ketone, okay? All right. And it turns out that you also have to have another substance in here, mercuric sulfate. I don't know the story here, but it's always hypothesized that someone broke a thermometer and when trying to do this reaction. Just water and sulfuric acid all by themselves do not accomplish the hydration usually, and it usually requires mercuric sulfate or mercuric acetate as a co-catalyst. Okay? All right. Ketones and enols are actually compounds in equilibrium, and we use this term tautomerism to describe constitutional isomers that are in equilibrium. And keto-enol tautomerism, we're going to revisit it in chapter 20, much far in your future. But remember that you've already seen this keto-enol tautomerism once, and it's connected with alkyne hydration. All right, this equilibrium, I can't really draw it to scale because in most cases what we're seeing is that the ketone form is greater than 99% of the form, and the enol form is less than 1%. There are a few exceptions to that, but in general, the ketone is the more stable form. All right, there we see a terminal alkyne, and remember the terminal alkyne addition, just like with the HX addition we saw previously, when we add it to the terminal alkyne, we can get regioselectivity favoring the Markovnikov product. When we take an internal alkyne, we don't get regioselectivity. So here's some examples down here. All right, and the top one here, and again, here we have the terminal alkyne, hydrogen right there. Okay, this produces the methyl ketone with a very high degree of selectivity. All right, here's an internal alkyne that's not symmetrical, so the two ends of this internal alkyne are different. And when we do the alkyne hydration, we get two different products. You will get both of these because both sides of the alkynes have alkyl groups on them. Never mind that this is a larger alkyl group than this one is. The fact is they're both alkyl groups. So you don't expect a whole lot of selectivity in this alkyne hydration right here. All right, the only time you can get selectivity when you have an internal alkyne is when you have a completely symmetrical internal alkyne like this one that has two cyclopentane rings here. So our alkyne hydration is going to hydrate both of these carbons, okay, but the product that you get turns out to be equal by symmetry regardless of which carbon that you add to. So this would result in a selective one. We're going to see more factors as the course progresses that lead to stabilization of carbocations, and there are cases where internal alkynes can be hydrogenated or hydrated selectively, but it has to be some sort of special mechanism for stabilizing the carbocation intermediate. All right, let's look at the mechanism for mercury catalyzed alkyne hydration. I'm going to use mercuric acetate because acetates are monoanionic salts, whereas the sulfate is a dianionic, and that can lead to confusion. All right, so what happens here is our initial addition is of the mercuric acetate to the alkyne, just like it was to the alkene back when you looked at alkene hydration. All right, so these three compounds here are all in equilibrium. Okay, this is probably the most stable one, the mercuronium ion or the mercury alkyne complex, but this is the second most stable, and this is the least stable because it's the primary vinylic carbocation. All right, so what we see here is that our more substituted carbon, it's got the higher degree of positive charge. Okay, so the water is now going to attack the place where there's more positive charge character. That's right here, and it's going to produce this compound. We're going to lose the extra proton and make acetic acid that generates the enol with a mercury on it, and sulfuric acid is going to turn the carbon-mercury bond to a carbon-hydrogen bond, and the enol that we initially get is going to turn into the ketone. Okay, mercury is an environmental hazard, and there's a lot of efforts going into producing better alkyne hydration catalysts. And I can tell you right now that if we look in the literature, gold seems to be the magic element here. We don't think of gold as being a reactive substance, but novel research into the chemistry of gold has shown that you can use gold as a catalyst to hydrate an alkyne as well. But mercury is actually more general, there's a longer history associated with mercury. All the nuances and factors about gold haven't really been worked out yet. Okay, so chemists are addressing this environmental hazard, and there's been some success in getting less toxic metals to catalyze the alkyne hydration. Okay, so I think this is where we're going to stop with this video. We're going to look at halogen and addition and ozonolysis and look at some more advanced organic synthesis problems in the next slide. Okay? Or the next video, sorry.